So the issue I'm having now is assembling the K global from the K element.
Okay. We'll review that a bit today. Yeah. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing? Good. Good. It's our last week together. So for this last week, originally, I think what I had planned for this week was just to have open office hours just for you guys to work on the projects. But I think it would be helpful for everyone. I mean, first of all, for us to finish the example that we did last week, but also just to kind of go over kind of the beginning parts of the project together. Just so that you know kind of what all the different data structures do, kind of what I'm expecting in different parts. Just because I've been getting kind of a lot of the same questions in office hours and emails and stuff like that. So my plan for today is I'm going to finish up. There's not that much more to do with the example. We're going to finish that up. I'm going to show you the MATLAB implementation. We're going to talk about kind of what part that goes into for your project, and then kind of just do a little bit of kind of introduction to kind of you know, at least the first part of the project in terms of what I'm expecting, and kind of, you know, get you guys going a little bit for that, just to kind of help answer, I think just some general questions that a lot of people seem to be having about the structure, about how to use certain things, and all that stuff. Okay. So I'm hoping that doesn't take the whole time today. I think that'll probably maybe take about 45 minutes. And then for the rest of class today, if you have questions on the project, if you want me to look at your code or anything, I'll go around and help you guys out with that. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So last time we were here, we were in the middle of an example. So let me actually scroll all the way back up here. It was quite a long example. Okay. And so actually, let me scroll up a bit further. Okay. So the entire week last week, we were working on this very particular algorithm on how to apply Gauss quadrature for a rectangular element. Okay. Because what we discussed last week was that, for a general finite element mesh, your elements are going to be of arbitrary shape and arbitrary size. Okay. They're all going to have the same number of sides, the same number of nodes, but how they're oriented, their exact size, how they're distorted and things like that. That's all going to be different. Okay. And so if you think about your final project, you're working with a triangular mesh, all the triangles are different. So they're all slightly different sizes, they're located in different places. But we still have to generate an element stiffness matrix for each of those elements. Okay. And so the way we do that, is to use this technique called Gauss quadrature, which is going to help us evaluate the integrals in our expression. Okay. So we started this example here where we have just a single rectangular element. I'm doing an example on a rectangle, but just note that your final project is a triangle. Triangles are actually a bit simpler. And so we kind of ran through the entire process here. Okay, so we had how many steps did we do? I think we did 9 steps, right? Yeah, we had 9 steps. Okay. So I'm going to go through the 9 steps just very quickly, just one more time. And then we'll kind of finish up the expression from there. Okay. Okay, so the way it works is this. So step 1 of the algorithm, and this is pretty consistent with your project code, is that you need to obtain the physical coordinates of all the nodes of the element. Okay. So for this particular element, we have 4 nodes, right? Nodes 1, 2, 3, 4. And so we need the physical coordinates of each of those: x1, y1, x2, y2, x3, y3, x4, y. Okay. And in fact, I think a lot of the confusion on the final project so far is how to actually obtain this information for each of the elements. So we'll definitely go over that later today. Okay. Okay. Then from there, you enter the Gauss loop. Okay. So this in green right here, you can see that I'm just saying that we're going to repeat all the following for each Gauss point. Basically, what I'm saying here is that we're going to enter the Gauss loop. And so in your starter code, that's the loop that loops over I_G. And once again, I'll show you where that is later on. But I just kind of want to make that clear. Okay? So everything below the green line will go inside the Gauss. Okay. Okay. The next step is that we need to establish the parametric coordinates of this Gauss point. Okay. So the whole point of the Gauss loop is that we're going to loop over each of the Gauss points. For this rectangle here, we have 4 Gauss points. So we have them separated each of those parentheses. And for this first iteration, we're going to choose that first Gauss point here. So -1/√3, -1/√3. Okay. Step 3, we're going to evaluate the shape functions at this Gauss point. So that's N1, N2, N3, N4. And remember, we're using the parametric versions of these. Step 4 is to compute the shape function derivatives at the Gauss point. Okay. So you can see we have 8 values here. So we have 4 shape functions and 2 derivatives for each shape function. So that's 8 values in total. Step 5 is to compute the physical coordinates of the Gauss points. And so for these, you're going to use the physical coordinates that you found in step 1, as well as the shape function that you just computed in step 3. Okay. Step 6, you're going to compute the Jacobian matrix. So there's a lot that goes on in step 6, but you're going to use a lot of the information that you computed previously to compute our Jacobian matrix. Okay. And then from the Jacobian matrix, you're going to compute the determinant of the Jacobian. That's step 6a. And then the inverse of the Jacobian, that's 6b. Okay. Next, you're going to take the product of your inverse Jacobian and your parametric shape function derivatives to get the shape function derivatives in physical space. So you're going to be performing this multiplication here. So again, it looks like a lot, but up until this point, you have those matrices already defined. So in MATLAB, you're just going to perform that multiplication. Okay. Okay. Step 8, you're not going to do this quite yet in the in part 1 of the project, but this is for part 2. You need to compute the value of the thermal generation function. Okay. Evaluate it at this Gauss point. And so again, you're going to be using the physical coordinates of the Gauss point that you found in step 5, plugging it into the thermal generation function, and you get that. Okay. And this is going to repeat for every single Gauss point. Okay. And so at that point, you're going to end the loop. Okay. And then once you kind of reach this point, you're going to basically form the element stiffness matrix from here. Okay. So the element stiffness matrix, you're going to take this product here of B underscore G. Remember, B underscore G, that was the shape function derivatives in the physical space. That was from step 7. You're going to multiply by the determinant of the Jacobians, which is step 6a. And then you're going to multiply by the Gauss weight, which is, the Gauss weight for that point. Okay. And then you're going to sum that up over all 4 of the Gauss, which for your triangles is going to be 3. Okay. Okay, so what I want to do today, let's start by forming the element forcing vector. Okay. So the element forcing vector, remember, there are 2 contributions to this normally. The first contribution that we normally have is from any kind of a body forcing term or any kind of thermal generation. So this is what you're going to do in part 2 of the project. And then the other contribution that can happen for some of the elements, if they're bordering a Neumann boundary condition, is that you're going to add contributions from that Neumann boundary condition. And this is going to be in part 3 of the project. Okay, so let's go over how to do the thermal generation function first. Okay. Okay. So for the thermal generation function, the way you're actually going to do this is actually very similar to how you did the element stiffness matrix. Okay. And so we have contributions from to the thermal generation term from all 4 of our Gauss points. Or 3, depending on if you're in a triangle. So just like we did with the element stiffness matrix, we just have to sum these up. Yeah. Okay. So just like we did with the element stiffness matrix, we're going to do a summation. And so the summation is going to be from G is equal to 1. In this case, it's 4. Okay. But again, for your triangles, it's going to be 3. Okay. All right. And so what we're going to sum up here is we're going to take NG. Okay. For NG right here, this is the values of the shape functions at the Gauss points. And so what step was that? That was step 3. We're going to multiply it by the value of the thermal generation function at that Gauss point. Okay. So this was the last thing we did before we exited the loop. So this is step 8. Then we need our scaling factor. We need the determinant of our Jacobian. Remember this one here, this is from step 6a. And then we have the Gauss weight. But for the algorithms that we're using for this class, the 4-point rule for the rectangle, the Gauss weight is 1. And then for the 3-point rule for the triangle, the Gauss weight is actually going to be 1/3. Okay. Okay. So that's part 2 of the project right there. So part 2 is to take, your contribution. So, if you're following this algorithm exactly, you already have it computed. You just need to kind of sum it up and add it to the element forcing. This FE is equal to this. Okay. All right. Any questions on that? Okay. So that's part 1, part 2. And so if you can get part 1 of the code, part 2 kind of follows kind of very, very closely after that. Part 1, part 2 are finished very quickly after each other. The hardest part of the code is part 3, which is the Neumann boundary condition. Okay. The reason the Neumann boundary condition is difficult is that, remember, not every element borders a Neumann boundary condition. And so the first thing we need to do is we need to determine if this particular element even borders a Neumann boundary condition. There's a way that we can do that in the code. Maybe we'll talk about it on Thursday, once more people kind of get to part 3. Okay. That's not the hardest part, actually. Because even if you determine if an element borders a Neumann boundary condition, the hardest part is you have to determine which edge or which side of the element actually borders that Neumann boundary condition. Because more often than not, only one side of your element is going to border the Neumann boundary condition. Sometimes there'll be 2, for a very kind of unique case, but for the most part, if your element borders the Neumann boundary condition, it's usually only one side. Okay. And so you need to determine which side of that element does that, and it actually matters. It does change how you compute things. Okay. So let's jump back into this example for a second. So if we look at the diagram for this element right here, okay, we can see that the Neumann boundary condition is being applied on the top edge of this element right here, right? Basically on this edge in between nodes 3 and 4. that means that when we do our you know, our contribution, we need to take that into account. Okay. Okay. Actually, let me redraw that down here. Okay. And so for our element, you know, our element current looks something like this. 2, 4. And our Neumann boundary condition is coming off the top, just like this. Okay. Remember, this element here is being mapped into an isoparametric element, right? And so it's being mapped onto something like this. Okay? Being mapped onto a perfect square. This perfect square has its origin right in the middle. And so if we were to just kind of visually kind of see, right, the top edge of that element is going to correspond to the top edge of this element as well. Okay? So what's unique about that edge? Or what can we say geometrically about that edge in the parametric space? Okay? So the Neumann edge, which is the edge between 3 and 4. Okay. What we can say about that edge is that it's a horizontal line, right? And so horizontal lines have a fixed value of the y component. Okay. And so what we can say is that on that entire edge, then the value of eta is actually fixed. So eta is going to be fixed at 1. Yeah.
Is that because our like domain is from -1 to +1?
Exactly. Yeah. So remember the parametric domain, the way that we set this up is that everything, all the corners are at values of -1. So node 1 here is -1, -1. Node 2 is a 1, comma -1. Node 3 is 1, comma 1. And node 4 here is -1, comma 1. Okay. So to evaluate our Neumann boundary condition term, we need to integrate over that edge, right? So remember for a 2D Neumann boundary condition, that is a line integral. Okay. When we integrate across this edge, we're basically integrating over this line right here. Okay. One way that you can interpret that is that we're integrating only in the xi coordinate, right? Because the eta coordinate is constant. So we're integrating from xi is equal to -1 to xi is equal to 1 with eta being constant. Okay. So that's really key. Okay, so you know, that basically tells us that we're only going to be performing a 1D integral, which is what we want here. Okay. So essentially the integral that we want to perform here is integral from -1 to 1. Okay. The integral that we compute for the Neumann boundary condition is n, which is our shape functions of xi and eta. Okay. So that one we're going to plug in our usual shape functions, but instead of integrating over both xi and eta, we're just going to straight up plug in eta is equal to 1. Okay. And remember, the reason we're doing that is we're only evaluating the Neumann integral on that top edge. And on that top edge, eta has a fixed value of 1. All right, and then the other parts of this is that we're going to multiply by q bar. Q bar here, that's the Neumann boundary condition value. So the Neumann value is you know, for our purposes, you can always assume that the Neumann value is going to be a constant, but just know that there are ways to make it so that your Neumann value is spatially varying. But for now, we're just going to assume that it's constant. I've kind of skipped a step here, but remember we're evaluating this integral using Gauss quadrature. Okay. And so we need to have our conversion factor here, or our Jacobian. And so our Jacobian in this case, remember for a 1D integral is the length of the line divided by 2. Because LE divided by 2 here is the Jacobian of that line. And then we're evaluating this integral over d xi. Okay. So that's the integral that we need to perform. Okay. But it's in kind of the perfect form for us. Right? So you can see that our integral is already from -1 to 1. So that means we can apply Gauss quadrature, and it's only in 1D. Okay? So we can apply 1D Gauss quadrature on this. Okay. So of course, you know, this is not the only integral that we can have. If your Neumann boundary condition was on, you know, on the bottom edge, then you eta is equal to -1. Or if it was on one of the vertical surfaces, it would change as well. The most important thing to know is that when you are performing a Neumann boundary integral, you're almost always going to fix one of the coordinates. And the main reason we do that is so that we can get a 1D integral. So maybe you're fixing xi is equal to -1, or xi is equal to +1, or eta is equal to -1, or eta is equal to +1. It really depends on the element's geometry. Okay. Question.
What if the Newman condition is on the diagonal?
Great question. So if it's on the diagonal, then it's you have to do another change of variables basically, because it's still a line, but you're on that diagonal line. So basically, on that line there's a fixed relationship between xi and eta. And so you just plug in xi is equal to -eta into the equation, and then integrate over that one variable. Yeah, that the instructions for that are in the project specs. I think probably we'll go over that together on. Okay, so let's see what that looks like for this problem. Okay. So I know this is kind of a strange example. We've been kind of learning theory at the same time as the example, right? But in order to do this, let's go ahead and plug it in. Let's plug in for it. Okay. And so first we need the length of the edge. So the length of the edge 3, 4. Okay. We're just going to use straight up distance formula for this. So we're going to do x4 minus x3 squared plus y4 minus y3 squared is equal to 0.06083. Okay. And so our Q value for that edge, I know it's I don't want to scroll all the way up there, but this Q value is it's 5. Okay. And so the integral that we're computing here is a integral from -1 to 1 of the shape functions of xi. Eta is equal to 1 in this case because it's at a fixed value, okay? Times Q bar LE divided by 2 d xi. Okay. Oh, we have a minus sign as well, just because of the just because of how it from the original weak formula. Okay. Okay, so we plug in for this, we get a minus. The length of the element is 0.6083. Okay. We're going to multiply by 5. We're going to divide by 2. And then we're just going to integrate the shape functions. Okay. Okay. So since this is a constant, you're integrating just a constant here. You can just use a 1 point. You can just use a 1 point Gauss rule. That's totally fine. But I'll show you what it looks like for a 2 point Gauss rule. And it's very sticky right now. Okay. All right, so remember for a 1D Gauss rule, xi1 is equal to, the first Gauss point is -1/√3, and the second Gauss point is a +1/√3. So we're going to plug that into the integrand there, which in this case is just the shape functions. Okay. And so if we evaluate that minus 0.6083 times 5 divided by 2, that gets us a minus 1.521. Okay. We have 4 shape functions. We have n1, n2, n3, and 4. Okay. So we're going to evaluate it at the first Gauss point. So that xi is equal to -1/√3. Xi is equal to -1/√3. Xi is equal to minus 3. That is equal to -1/√3. Okay. Eta is going to be equal to 1, right? That's one vector. We're going to add the same vector, but instead we're going to evaluate xi at +1/√3. And then once again, all the eta values are just going to be. Okay. Once again, everything in this parentheses right here, this is just 1D Gauss quadrature. And we're only going to apply it on this on the xi. Okay. And so we plug all those in, and so it's a little tedious plugging in. But what you're going to get actually something like this. And so we're going to get minus 1.521. Okay. We plug in everything for all four shape functions. We perform the addition and get 0, 0, 1, 1. Okay. So I want you to notice something about this because it's a very interesting observation, right? Remember that this Neumann boundary condition was taking place between nodes 3 and 4, right? If you look at the structure of this vector that comes out, you can see here that we have zeros for the first two, and the first two correspond to nodes 1 and 2, and we have ones for the last two entries, which is for nodes 3 and 4. Okay. This makes sense, right? Because the Neumann boundary condition is only being applied on those nodes, essentially, right? Or in between those nodes. So it makes sense that the only active participants in this are going to be on the nodes that straddle the Neumann boundary condition. And of course, we can distribute that so that minus 1.521 can just be distributed throughout. And so we get 0, 0, minus 1.521, minus 1.521. All right. Any questions on that? Okay. All right. So let's look and see how all this is implemented in MATLAB. Okay. So this next part, I'm showing you code that is quite similar to what you're going to do in your project. Okay, so let me go ahead and share my screen. So this is a code that I posted on Canvas. So this is called Isoparametric example. Okay. So basically, this is just the MATLAB implementation of the example that we just did in class. So this is for a rectangular element. So you can see here that this is an isoparametric approach for a 4-node quadrilateral, and we're going to compute the element stiffness matrix and element forcing vector for this element. Okay. And you can see that the way that I've factored this code is that I've kind of gone, through our 9-step algorithm. Okay. So first thing that you're going to notice in the code here is that we obtain the physical coordinates of each of the nodes in this element. Okay. So you can see here we have x1, y1, x2, y2, x3, y3, and x4, y4. Okay. For this particular example, since we have just one element, I've just hard-coded the coordinates in there. But of course, in the project, there's a different way to obtain these coordinates, which we'll talk about in a bit. Okay. So this was step 1 of the algorithm that we went over in class. Okay. Okay. And then for the project, of course, you would obtain the nodal coordinates from the nodes matrix. Okay, which we'll go to later. Okay, so next thing that we're going to do here is we're going to put these parts here are optional, but I just find it a little bit easier to work with. So I put all the physical coordinates into a single matrix. Okay. You don't have to do this. I just do this just to kind of clean things up. Okay. And next thing that we do is that we list out the Gauss points, okay. Just so it's kind of easy to refer to. So you can see that the first Gauss point is minus 1 over root 3, comma 1 over root 3. The second Gauss point is positive 1 over root 3, comma minus 1 over root 3, and so on and so forth. Okay. So next we enter our algorithm loop. So this is when we kind of go the step-by-step process. So if you go back to our notes, this is when, we start the Gauss loop. Okay. So this is IE Gauss. Okay. And so from here, we're just going to go through the algorithm itself. So you can see here that every step of the algorithm that we went over has kind of a corresponding code for here. So just so that you can kind of see how it looks. Notice that the numbering is off a little bit just because I added, just for this class, I added step 1 is obtain the coordinates, just because that is an important part. So I'm just going to renumber these as we go. Okay. Okay, next we have step 2. So step 2 is to establish the parametric coordinates at this Gauss point. Okay. So notice how we're looping over the Gauss points, and I've created this matrix here to reference each of the different Gauss points. Okay. And so this just obtains. So on the first iteration, this value here is going to be minus 1 over root 3. And this one right here is going to be a minus 1 over square root 3. But just know that each loop iteration is going to change to the other Gauss coordinates that we have up here. Okay. Okay. So now that you have the Gauss coordinates, the next step is to compute the values of the shape function. So this is step 3. Okay. So you're just going to plug in the xi and the eta. Here I call it eps for epsilon, but epsilon, xi, they always look very similar to me. Okay. And you're going to plug those into the shape functions themselves. So n1, n2, n3. Okay. You can put them into a matrix if you want, or put them into a vector, but it's not necessary. Step 4, we're going to compute the shape function derivatives. Okay. And so we have the shape function derivatives with respect to xi or epsilon, and the shape function derivatives with respect to eta. And so if you check back in your notes, you can see that these formulas line up exactly with what we have in the notes. And just to make things more convenient, I've also put it into a matrix. Okay. Step 5 is to compute the physical coordinates of the Gauss point. And so here we're going to use a combination of the physical coordinates of the element of itself and the shape function. So we have x1, n1, x2, n2, x3, n3, x4, n4, all added together. And then y1, n1 plus y2, n2 plus y3, n3 plus y4, n4. Okay. Again, this is exactly as what we have in the notes, but this is just kind of in code form here. Step 6 is to compute the Jacobian. And so remember step 6, there was kind of a lot going on. But now that we have all the matrices computed, we can just compute them easily with some commands here. Okay. First of all, the Jacobian is the shape function derivatives multiplied by the coordinate matrix, which is all the x1, x2s. Okay. Then you can take the determinant. Taking the determinant in MATLAB is easy, so you just use the command det and feed in the matrix that you just computed. And then we also need the inverse, or the Jacobian inverse. And once again, there is a convenient MATLAB command for that, which is inv. Okay, so use inv of Jacobian. Okay, step 7, you're going to compute the shape function derivatives in the physical space. And so that is this one here. Okay. So you're just going to take the product of the Jacobian inverse multiplied by the shape function derivatives in the parametric space. So that was step 4. Okay. Step 8, we compute the thermal generation function. And step 9, we just add it all together. Okay, so step 9 is just adding those contributions. Okay. All right, looks like I don't have the Neumann boundary condition here, but I can make a script for that if that would be helpful. Okay. All right, and so that's basically, there wasn't that much to talk about with this code. It's basically just kind of line from line exactly kind of what we did with the algorithm, except you have to put it in kind of proper MATLAB syntax. Okay, so a lot of this code right here, you can use the general structure for it for your final project. Of course, the only thing with your final project is that you're working with triangles, not rectangles. Okay, so the shape function is going to be different, and you're only going to have 3 shape functions instead of 4. All right, any questions on this? Yeah.
You're going to go over how to get the physical coordinates using the nodes matrix.
Yes.
Right?
Yeah.
Okay.
We'll do that. I want to talk about triangles for a little bit first, and then we'll go over the start.
Okay. Okay.
Yeah. Mm-hmm. All right, so I would definitely keep this on hand, especially as you're doing part 1, part 2 of the code, because it's going to be quite similar to this. Yeah.
Sorry, you did say mention that you might make a non-condition code for this.
Yeah, I think I will. So I think probably what I'll do tomorrow, because we did a Neumann boundary condition for this problem, but I don't have the code for it. So I'll show you what that looks like. I'll do this. Yeah. Okay, so let's talk about triangles. Let me come back to the iPad here. Okay, so all the theory that we've been talking about, for the last, all of last week and all of today, corresponds to rectangular elements. Of course, for your project, you don't have rectangular elements, you have triangles. So let's talk about some of the differences, what that entails. Okay. So the entire algorithm that we just went over, that we spent almost 2.5 classes talking about, that can be applied to triangular elements as well. Okay. But of course, there are a couple changes that you have to make. One of the most obvious changes is that, instead of 4 nodes per element, you have 3 nodes. Okay. So that means you're going to have 3 shape functions, 3 physical coordinates, and whatnot. Okay. That one's pretty easy. That one's not, too difficult for people to figure out. Okay. The second one that could throw you for a loop is that the shape functions are different. Okay. In fact, the shape functions are actually much simpler for the triangle than they are for the rectangle. So let me go ahead and list them for you here. So the shape function n1 of xi and eta is simply just xi. Okay. N2 of xi and eta is just simply eta. Yep. And then N3 of xi and eta is 1 minus xi minus eta. Okay. All right. One thing that you might notice, and actually a few people have noticed this already, is that because the terms here are either perfectly constant or perfectly linear, when you take the derivatives of this, the derivatives only give you constants. You can use that information to your advantage in part 1, if you want. But it's also perfectly fine to not make use of this information. So you can do the entire part 1 of the code without this knowledge, and you'll get the right answer. In fact, that might be the better way to go, just so that you get practice with the you know, with the whole algorithm, because you're gonna need to implement the whole algorithm for part 2 anyway. So make use of the information how you will, but no, you're not tripping over yourself if you take the derivatives and you just get a constant. Okay, that's different than our rectangles. Remember when we took the derivatives of our shape functions for our rectangular element, we still got functions of xi and eta, because the rectangle has that extra cross term to it, but that's not the case for the triangle. Okay. And the number 3 difference here is that the Gauss points or the Gauss quadrature points are going to be different as well. All right, so when you're performing your Gauss quadrature, the Gauss point locations are going to change and the weights are going to change as well. All right, so let me show you a figure just to kind of show you what the Gauss triangle would look like. Okay, so the Gauss triangle looks something like this. I believe this is node 1, node 2, and node 3. Okay. And so typically, so there's technically multiple different Gauss rules depending on the accuracy that you want, but for most cases, it's best to use as just a 3-point rule. And so your 3 Gauss points in this case are the following. So Gauss point 1, the GP1, we have xi1 is equal to 2/3. Eta1 is equal to 1/6. Okay. So roughly that's maybe around maybe like right here. Okay. So this right here would be GP1. Okay. But the most important point which is different than the rectangle is the weights. Okay. So the weights we kind of brushed off on the rectangle just because all the weights for the 4-point rule were 1. Okay. But for the triangle, all the weights are actually 1/3. So just remember when you're summing up all the contributions from the different Gauss points, you divide each contribution by 3, or you divide the whole thing by 3. Okay. So let's look at Gauss point 2, GP2. So Gauss point 2 is like the mirror image of this. So we have 1/6 for xi1. Sorry, this is xi2. And then eta2 here is 2/3. And the weight for this one is also 1/3. Okay. So visually, that's probably somewhere like right here. This right here is GP2. Those are rough locations, they're not kind of exact. And then Gauss point 3 is xi3 is equal to 1/6, and eta3 is equal to 1/6. Okay. And the third Gauss weight is 1/3. Okay. And this Gauss point, you can probably guess, probably right in this area right here. Okay, so it's GP. Okay, so when you're doing Gauss quadrature for your triangles, make sure you don't use any 1/√3. So the Gauss points are changing. The triangle is a different shape. Okay. Okay, but those are the 3 main differences. But the general structure of the algorithm, the exact steps that you follow are all the same. It's just that when you go and do things that involve the shape functions, or when you go and plug in the Gauss points, make sure you make the appropriate adjustments for the triangle versus the quadrant. Okay. All right. Any questions on this? Nick, to kind of answer your question, we'll go over it in a bit more detail on Thursday. But if you do have a Neumann boundary condition on this edge right here, right? notice how that edge, that the diagonal edge connects nodes 1 and 2, right? And so even after you perform the Gauss integral, that line integral on that edge, you're going to end up with a vector that looks like this, 1, 1, 0, because it connects 1 and 2. There's a longer explanation that involves, doing the parametric change of coordinates and the integral, but that's kind of what you get in the end for this particular case. Yeah. Okay. All right. So the last thing I want to do today is to go over the starter code, just so that just kind of help everyone kind of get started. So let me kind of bring that up again one more time. Sorry, this took a little bit longer than I thought, but I want to make sure I go over everything kind of carefully. Okay. So this is part 1 of the starter code that's online. And actually, let me go ahead and run this part of the code here just so that you can see. That part, this part as well. Okay. So if you go to part 1 of the code, right? The first thing that you need to implement are the Dirichlet boundary conditions. So, I'm not going to spend too much time talking about this because we've done this before. So this is basically the same way that we did our direct stiffness method. So you need to indicate which edges the Dirichlet boundary conditions will be applied to, as well as their values. Okay. Yeah, question.
Just to be clear, this is going to be like a 1x4 matrix or vector, right?
Yes, I believe so. I forget exactly how many Dirichlet boundary conditions, but if there's 4 of them, I think it's the 4 outer edges.
And then the entries are just literally the number of the edge, and the other one is going to be the values.
Exactly. Yeah. So let's say that you're applying the boundary conditions on all of the outer edges here. You enter 1, 2, 6, and 7, and you don't have to add E1, E2, E6. You just do, for instance, this would be 1, 2, 6, 7, just like that. Yeah. And then the next vector would have the actual value of the Dirichlet boundary condition. Okay. But the main thing I wanted to discuss today was actually these 2 vectors. So these 2 vectors are actually kind of the biggest key that you're going to use here. Okay. The first vector, or the first data structure that we have here is called the nodes matrix. And if you read the tooltip next to this matrix here, you can see that this array holds the XY coordinates for every node in the mesh. Actually, let me do this just so it's a little bit easier to visualize. Let me make the edge a little bit bigger, and let me kind of rerun everything from that. Yeah, with 0.5, it's a little bit hard to visualize. It's a little bit. Okay. So let's maximize this one. All right, so if you look at this diagram here, so this diagram is figure 3. So this pops up every time you run the code. You can see here that this is our mesh, right? So you see all the triangles. You can see that the triangles are different shapes. And each of the triangles, or each of the nodes, I should say, has a number associated with it. Okay? So let me zoom in on this element right here just so you can see. Okay? So you can see that each node here has a number. So this is node 165. This is node 196. And 195. Okay. And if you move around to a different element, you can see that all the nodes have a different number. Okay. So all of the nodes in the mesh have a unique ID number that identifies. Okay. Remember, one really key point in our algorithm is that we need to know the exact physical coordinates of each of these nodes, the X coordinate and the Y coordinate, right? How do we obtain those? And so we can obtain those using this nodes matrix. Okay. So if you look at this nodes data structure here, you can see just based on the workspace that it's 2 by 220. Okay. So that means there are 2 rows and 222 columns. Okay. If you count the number of nodes in this mesh, so let me kind of back it out here just so you can see the whole thing. Okay. If you count the number of nodes in the mesh, that there's going to be exactly 222. How do I know that? It's because the number of columns in the nodes matrix is 222. Okay, so let's look into that data structure there and kind of see what this whole thing is about. Okay. All right, so just like it was advertised, there are only 2 rows, but 222 columns. Okay? So the way to read this is that, each column represents a specific node with that exact matching ID number, okay? And the 2 entries in that column, the first entry, the first row, and the second row, that represents the X and Y coordinates of that node, okay? So let's scroll over here. So let's look at node 82, okay? And so node 82 has an X coordinate of 0.1279 and has a Y coordinate of 0.1510. So actually, let's see if we can find that node. Let's see. So it's 1, 2. What did I say? Node 82, right? So node 82 is right about here. Yeah. So if you look at the physical coordinates of the node, and this zoom thing is always in the way, okay, you can see that the X coordinate for the node is like 0.128 maybe, and the Y coordinate is 0.153, something like that, right? Just visually. And you can see based on the nodes vector that this is exactly the case, right? So I was a little bit off because my vision's going bad, but but this nodes vector has all the XY coordinates. Okay. Now the question is, how do we make use of this, right? Because this is great, right? So we have all the XY coordinates, but we need to actually be able to make use of that in our algorithm. Right? Okay, so if you scroll down a little bit, you can see here that this is the main loop. Okay, so the main loop is going to loop over all the elements and compute the element stiffness matrix for each element. Okay, part of that is that we need to obtain the XY coordinates for each node in this element. Okay, so how are we going to do that? Let me bring up another figure here. Okay. So in addition to the nodes having unique ID numbers, the elements are also going to have their own unique ID number as well. Okay, so if you zoom in, let's zoom into this part right here. Okay, you can see that each element here has its own unique ID. So this is element 25, element 117, element 108, okay, and so on and so forth. Okay, so the mesh actually knows which nodes are connected to which element, right? So for instance, let's say that we're interested in the nodes connected to element 108. Okay. So one way that we can do this, and this is the way that we've been doing, for all of our direct stiffness problems, if we just look at it visually. Okay. So actually, let me do an easier one. Let me do element 91, the one that's right here, right? And so if we look at element 91, oops, not this one. Right. Visually, we remember that element 91 is the element that's right on top of this kind of red rectangle here. Okay. And so visually, we can see that the nodes connected to element 91 are node 7, node 4, and node 75. Okay. So, how can we make use of it? Because obviously we're not going to look visually at all, so many elements. Well, we have our connectivity matrix. Okay. So if you look at the connectivity matrix, you can see that it is a 3 by 374 data structure. Okay. And the way to read this is that, if you go, the columns represent the element ID number, and the rows represent the nodes that are connected to that element. Okay. So what do we say? So that the element that we're interested in, that is element 91. So let's go to column 91 of this data structure here. Okay. So column 91. And you can see the connectivity matrix has 75, 7, and 4, which are exactly the 3 nodes that are connected to this element, right? 75, 7, and 4. Okay. So in order to get the physical coordinates of the nodes in each element, it's actually a 2-step process. So the first step is to use the connectivity matrix. Okay. So on this to do, it says to obtain the node indices for this element. Let me add a caveat to this using the connectivity matrix. Because you need the nodal ID numbers to access the nodes vector. Okay. So usually I do it something like this. So I do N1 or IND1, whatever we want. We do connectivity. Okay. We want the first node, right? So the first node, remember the structure of the connectivity matrix, has 3 rows, and the number of columns represents the number of elements, right? So the way we're going to access this is that we're going to do row 1, and then the element that we're accessing is going to be referred to by the loop index, right? Because we're looping over every single element. So it's 1 comma I underscore e. Okay? And you're going to do the same thing for 2 and 3, but I'll let you guys copy and paste that. Okay. Now, question, yes.
Does it matter which, like if we're looking at the actual diagram, does it matter which node goes where?
It doesn't.
No?
So you're gonna use all 3 of them anyway,
Mhm.
and so it doesn't really matter which one. Yeah. If you're as long, I mean, you're gonna be, because you're doing it in a loop, you're doing it in a consistent order anyway.
Mhm.
Then it doesn't matter.
Okay.
Okay, so then how do you make use of this in the to get the coordinates, right? So let's say you want x1, x2, x3, and y1, y2, y. Okay. So let me add a caveat note here. So this is going to be using the nodes, quotes, nodes matrix. Okay. So let's use the nodes matrix. So x1 here is going to be nodes. Okay. Let's remind ourselves of the structure of the nodes matrix. So the structure of the nodes matrix is has 2 rows. Okay. The x coordinate is in the first row and the y coordinate is in the second row. So it's going to be nodes first row. And the column here is going to we're going to use the ID number for that particular node. So it's going to be IND1. Okay. So that's the x coordinate for node 1. Okay. Similarly, for the y coordinate for node 1, we're going to do nodes 2, comma IND1. Okay. 2 corresponding to the second row, which is the y coordinate, and IND1 corresponding to the ID number of that first node. Okay, so I think that's probably the most common question I've gotten over the last couple of days, but so hopefully that kind of clears things up in terms of how to use those 2 things. Okay, we haven't seen the last of connectivity, and so we're actually going to use the connectivity matrix again in the assembly, which I did want to talk about briefly today as well. But from here, you're going to do this is the Gaussian. Okay. So I'm not going to go over this again just because we already covered this kind of earlier today. But of course, you would have to modify the algorithm that we went over today for a triangle. Okay, and I have some tips here to help you out. You don't have to follow these tips. There's other ways to do this. If you have different preferences, or if you prefer to kind of be a bit more explicit with your calculations, that's fine. I just have these tips here just to guide you if you're a bit. But of course, these tips are all based on my own programming stuff. So, and everyone programs. Feel free to change this. Okay. But any questions on just the connectivity matrix and the nodes matrix and kind of what they do? Okay. Okay. So other thing I want to do here is that we want to do assembly. Okay. I'm not going to go over the Dirichlet boundary condition because that's almost exactly the same thing as our direct stiffness method. But it would be good to kind of review the global assembly. Okay. So we need to assemble the global stiffness matrix from here, and that involves obtaining the loading in all the element stiffness matrices and inserting them in the right locations. Okay. So there's 2 parts of this, if you remember. So the first part is we need to compute the element stiffness matrices, which we've done. But if you're going to do it in a separate loop like this is how we kind of traditionally did it in direct stiffness, you need to reobtain it. Okay? So you need to load in the element stiffness matrix associated with element I underscore E. Okay? Where I underscore E is the index for the loop that we're running. Okay. Okay. So that part pretty easy. Okay. Number 2. The other thing that we need to do is that, in order to put things in the right place, we need to know which nodal ID numbers are connected to this element. Okay. Because if you think back to our direct stiffness method, right? Of course, our meshes in that unit looked a lot different. But if you remember, if we had like say like a truss structure that looks like this, right? We had kind of fixed supports here, fixed support here. Okay. And we had forces like this, right? Each of these nodes also had its own ID number, right? So this is node 1, node 2, node 3, node 4. Okay. If you remember back then, the main purpose of these nodal ID numbers is to tell us which rows and which columns in the global stiffness matrix we're going to insert that entry, right? So let's say we're going to do it for this element right here, right? So this element is connected to nodes 2 and 3. What that tells us is that in the global stiffness matrix, right? This element here, we'll call element B, is going to be inserted into, column 2, column 3, row 2, row 3. So something like this, okay? So we're going to use that exact same logic here, okay? Except, of course, we have way more nodes here than we did back then. Okay. So the next step here is to get, the ID numbers that are connected to this element. Good thing, we already have a data structure that allows us to do this, which is the connectivity matrix. So you're going to use the connectivity matrix again in this loop in order to find the appropriate places to do it. Okay. Okay. And then step 3. Now that we've kind of obtained our element stiffness matrix, and let me just remind you that this element stiffness matrix is a 3x3. Okay. We're going to insert the element stiffness matrix from step 1 into the appropriate locations in K global using the ID numbers from step 2. Okay. So if you remember from our direct stiffness, unit back then, we wrote something like this, right? So K global, okay, and let's say IND1, comma IND1 is equal to. Remember, we don't want to overwrite it, so we want to just add to it, right? Because every node is going to have contributions from multiple elements. So we do K glob IND1, comma IND1 plus. And I'm basically writing the code for you. So I'm going to stop here, but I'll do something like that. Okay? Where that ... there is going to be replaced by the appropriate location in the element stiffness matrix. And you're going to repeat this 8 more times. Because the element stiffness matrix is 3x3, so that means there's 9 entries. So that means there are 9 entries you need to add to the global stiffness. Okay. All right. Any questions on the assembly there?
Can you just repeat that last part that you said about repeating it 8 times?
Yeah, because so the way at least the way that I usually implement this is that I add in basically entry by entry of the element stiffness matrix. And so your element stiffness matrix for a triangle, because it's a 3-node triangle, is 3x3, right? So we have 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So this line of code here is only gonna add the contributions from this into the global stiffness matrix, right? So it's only gonna be 1 entry. So you need to repeat this 8 more times for all the other entries in this matrix, making sure that each one goes into the appropriate location. Yeah.
This section also mentions the forcing vector. I thought that was part 2.
Part 2, yeah, forcing vector is part 2. Yeah, so the only contributions to the forcing vector in part 1 is going to come from the Dirichlet boundary conditions. Okay. But yeah, there's no thermal generation part 1, so only part two will have the forcing. But same thing, so for the element forcing vector, you're gonna use the connectivity matrix and use that to find the appropriate location in the global.
Alright, so we can just ignore the part which says and global forcing vector.
I might have just included that by mistake. Oh, yeah. Yeah, so this part here is for part two. I think what I did is I have one code that does everything, but then I split it up into different starter codes. I just but yeah, you do both in the same. That's why I have it. For part one, you can ignore this. All right, any other questions on this? Okay, so I'll leave it here for today. So on Thursday, what I'll do, well, tomorrow, what I'll do is I'll write a script to show you how to implement the knowing boundary condition. And then we'll talk a bit more about how to implement that in the project, because that's probably the hardest part. All right, so thank you guys for coming today. Hopefully this was helpful for you guys for the project. So I don't think I mentioned at the beginning of class day, but obviously I have office hours this week because it's the last week of lecture. I will have office hours next week because I know you guys will be working on the projects. The office hours next week will be at the usual times, but they're going to be virtual only. And so please log on to Zoom. And because we're going to have the project due on a Monday, May 20th, I'm going to have office hours on that day as well, but also just virtual. Okay. All right, so thank you guys for coming. Make sure to reach out to me if you have questions on the project, and I will see you on Thursday. Yeah.
So you said elements of the matrix.
Yes.
Tomorrow.
Yeah.
I'm so
Yeah.
fun, dude.
Oh, when did you start?
Saturday.
Oh,
Yeah.
wow. Because we have like
For this
one
Yep.
I mean,
on that matrix.
pretty
We had one. So it's pretty easy to split this.
It's so-
Yeah. Green nodes. The question is, how do we split the middle contribution?
Yeah, so the reason we put that up with the frame because it was 36 hundred. Like I did like it's just.
The other.
But for 3 by 3, you just do kind of just 9 by 3.
Yeah, that makes sense. Is node.
Yeah. No, that's part of like that section, right?
It's the same. So whatever nodal ID number that we have in the connectivity matrix, that's the exact row and column that's going to be the one. Yes, that's those. So those nodal IDs, they serve quite a few purposes. So for our assembly, the ID numbers also refer to this exact row and column. That's what this is basically. So this IND1, the IND1 you compute in the connectivity matrix. We're adding this to the IND1 row and the IND1 column. So that ID number also corresponds to the same row.
That's a lot easier than I was thinking. Okay, that's, I think I got it. Thank you.
Yep.
So like here where you say the elements of the matrix, the element.
Yep.
What does that mean? Does it mean we just recall it in this?
So in this loop right here, you're going to be computing KLM, right?
Yeah.
So KLM is a 3 by 3 by, and so it's a three-dimensional one.
Okay.
And so we're saving that outside. So here I'm just load it back in. So you computed in the previous one. So if you look back to our codes for the frame and the truss, you see there's one line where I say KE is equal to KLM for this particular element. Right? So that's all that is. So look back at our previous code and you'll that line will make almost.
Okay, sounds good.
Yeah. Yeah. Sure. What's up?
Sorry, I missed last week. Do you have the midterms?
I forgot today. Okay, I'll bring it Thursday.
Okay.
Or if you want to follow me back to my office right now, right after this, then I can give it to you.
Okay, yeah, that's fine.
Okay.
Do you mind scrolling up a little bit?
Sure.
So I can see the first part. Again, I just want to make sure I got it right.
This part here?
Just, yeah.
Okay.
Thank you.
Yeah. Yep.
no request here, it takes, basically it's just a number of nodes, like.
Exactly.
How does it calculate how many nodes are there? It's just based on the.
Yeah, so then we're using some pre-built functions in that.
Okay, so
It's-
basically from this.
Yeah.
this thing.
Normally, yeah, you're right. That's not trivial. That's hard to do, but we're kind of taking some shortcuts from that. Yeah, from that method.
And again, this thing also, I think the ratio is more, more better to do.
Yeah.
Than the what I thought, because this thing is more simplified basically.
It's a bit more explicit, but both will work. So. Yep.
It's easy to follow. Yeah. Okay, thank you, Russell.
Yep. See you guys.
So say you go on person.
Yes, Thursday will be in person. Thursday will be the last in person also.
Okay.
Yeah. Mhm.